Can you all hear me? Can you all hear me okay?
Good morning.
Morning. Alrighty. Um, so here are the current assignments. So tonight, okay, is due. I have the right. Tonight is due the focus problems, the word problems on quadratic functions. So on page 273 to 280, number 24, I copied it out of the ebook, so it's right here. If you have a hard time finding it. And, in section 3.1, number 64, there's a problem there as well. So that's due tonight. And, you also had section 3.1, the first go at it, due last night. So I'll get that graded for you today, hopefully, and get it back to you. And, we have the assignments for 3.2 and 3.3 here. We still need to go over some more stuff for section 3.3. And I'll post something for section 3.5 after class. Discussion problems for sections 3.3 and 3.5, they're right here. There are no discussion problems on the syllabus for 3.3 and 3.5. There's just this sort of extra set of notes. But I didn't like it too much. I think that the topic deserves at least a little discussion and some problems to work on. So so we'll work on these problems, and I'll have a hand-in assignment for those as well. All right. So section 3.2 we went over already. Yeah, graphing polynomial functions. We talked about that, graphing of polynomial functions. So let's go to section 3.3 and talk about more about division of polynomials. All right, so the ones I assigned were 3 to 23 odd. So let's look at number 15. So perform the following division operation. Okay, so find the quotient. And remainder. And write as, right, so p of x over d of x is equal to, so you get a quotient plus a remainder over the same divisor. So if you have a polynomial divided by another polynomial, d, so p divided by d, you write it as quotient, q of x, plus remainder over the divisor again, or denominator, if you will. So that's the quotient, and r of x is the remainder. All right, so we're dividing x squared minus 3x plus 7 by x minus 2. So Step 1, first iteration of the division process. What do I need? You look at the leading term for each polynomial, right? And you want to multiply the divisor by something so that the leading term becomes x squared. And that's just going to be x, and that's your first term in your quotient. So multiplying this by x, you have x squared minus 2x, right? And you want to subtract that, right? I want to take x squared minus 2x and subtract from this. So what you're going to do is negate this polynomial. Multiply it by -1 and then add. Multiplying by -1 just involves flipping the signs. So first sign becomes negative, second sign becomes positive, right? Right, it starts out like this, right? This times x is x squared minus 2x. These leading terms match up. Now I want to subtract, so I flip the signs and add. So this one is 0, minus 3x plus 2x, minus x plus 7. What do I need to multiply x minus 2 by to get minus x? Well, minus 1. So that's the second term in my quotient. So then multiplying this by -1, I have minus x plus 2. Flip the signs. I want to subtract, right? The leading terms match up here, but now I want to cancel it out, so I need to subtract. So flip the signs. So this negative here becomes positive, and this positive here becomes negative. And now I add, and I get 5. And now this has degree 0. This has degree 1. So the degree of the divisor is 1, and the degree of this remainder. So at each step, the result that you get after doing that subtraction, flipping the sign and adding, that's called the remainder at that step. And you want to keep going until the remainder is as small as possible. As small as possible is when the degree of the remainder is strictly less than the degree of the denominator. The degree of the remainder is strictly less than the degree of the divisor. Denominator, yeah, divisor or denominator. Either term works. Right, because I can't multiply this by anything to get 5. Right, at each step you want to multiply the divisor by something to cancel out the first term of the remainder at each step. But that can't be done here because the degree is too small. So then, once you've done that, this is the quotient, and that's your remainder. So, therefore, this original fraction is equal to the quotient x minus 1 plus the remainder 5 over the divisor x minus 2. You know, if you want, so this is your final answer here. If you want, one could actually check it, right? I can add these guys back together. X minus 1 plus 5 over x minus 2. Well, I need a common denominator to add those guys together. So this is x minus 1 times x minus 2 over x minus 2 plus 5 over x minus 2, right, is equal to, so this is x minus 1 times x minus 2 plus 5 over x minus 2. So this is x squared minus 3x plus 2 plus 5 over x minus 2. So this gives me x squared minus 3x plus 7 over x minus 2. So that checks out, right? That's the original fraction we started with, the original rational function. Okay? So, I mean, you don't always have to perform that check. First few times you do it, maybe it's nice to do that check to make sure you're getting things right. But it can be an awful lot to actually do it sometimes. All right, 17. So same directions. 4x to the third plus 2x squared minus 2x minus 3 over 2x plus 1. All right? So we want to do this division here. So I'm dividing the numerator by the denominator. So what do I need to multiply the leading term here, 2x, to match the leading term here, 4x to the third? What would be the first term in my quotient? Is the factor I need to multiply 2x by
2x squared.
2x squared. Right? 2x squared times this, right, is 4x to the third. Right, so this is actually easier than doing the long division of numbers base 10, because there's no carrying, there's no multiplication of large numbers together. You know, it doesn't deal with, you know, some of the sort of tedious bookkeeping aspects that base 10 arithmetic does. So it actually turns out to be easier. I mean, one can make mistakes just here as well, but you know, in some ways it's easier. So multiply this by 2x squared, so we get 4x to the third plus 2x squared. And now I want to subtract, so I flip the signs here. So this is minus and that's minus. Now I add, right? This is just 0 here, right? But now I got to bring down these two terms, minus 2x minus 3. What do I need to multiply here 2x minus 1 by to get 2x equal to minus 2x? Well, just minus 1. So that's the second term in my quotient. So minus 2x minus 1, I want to subtract this, so I flip the signs, and I get minus 2. And that's my remainder. Right? This is degree 1, this is degree 0. So that's my final remainder. So remainder quotient. So final answer is as follows. This is equal to the quotient 2x squared minus 1 plus minus 2 over, well, maybe we should just make it minus. That's fine. Plus minus 2 over 2x plus 1. Okay. And what that does, you know, it gives you a polynomial plus a rational function over the same denominator, over the same divisor, but the degree of the top is less than the degree of the bottom, right? So that's more of a normalized form for a rational function, where the degree of the top is less than the degree of the bottom. And in section 3 the next section we're going to, well, no, 2 sections from now. Section 3.6, you'll see why that's helpful. One way it's helpful. There's other ways too. So 19. Oops, my book here. So x to the third plus 2x plus 1 divided by x squared minus x plus 3, like that. So do our division here. By the way, the difference in the degree of the top and the degree of the bottom. So what's the difference here? The difference here is 1. Right? So at most, you'll go through 2 iterations. Here, the difference in the degree of the top and the bottom is 2. So at most, you go through 3 iterations. This one, the first one, the degree of the top and the degree of the bottom, the difference is 1. And you go through 2 iterations. So the difference in degrees is the number of iterations minus 1. The max number of iterations. It could be fewer. Could be fewer. But at most, the number of iterations at most. So at most, we're going to need 2 iterations here. Basically, because the degree of the remainder goes down by 1 each step, until the degree of the remainder is less than the degree of the bottom of the divisor. Goes down by 1 or more than 1 because you're always canceling out that leading term. Oops. X to the third. Now, by the way, you're missing the squared term here, so you might want to leave a gap. Right, we're missing that squared term here, so maybe we're going to leave a gap there, okay? Because we want to make sure we're subtracting like terms. So leave a gap for missing x squared term. All right, so I want to multiply this by x to get x to the third. So this gives me x to the third minus x squared, right? So the x squared goes here, where this is supposed to be. So you either leave a gap or you put in 0x squared. Right? You could do this, 0x squared. Let's do it that way. Why don't we do it that way? X to the third plus 0x squared minus x plus 3. So make sure don't leave any missing terms. Use 0x squared for the missing x squared term. Or you can leave a gap. I don't know. I mean, however you like to do it. This is maybe more explicit. So x to the third minus x squared plus 3x. Okay, now I want to subtract that. All right, so to subtract, I flip the signs. This is minus, plus, minus. Okay, don't put the minus here, by the way. Okay, you have to take x and multiply it by this. Gives me x to the third minus x squared plus 3x. But I want to subtract that. So in order to subtract it, I flip the terms now. All right, add this together, and that gets rid of the x to the third term. And then the x squared term, I just have one of them, right? 0x squared plus x squared. X minus 3x, that's minus 4x plus 3. All right, so here the degree here is 2, the degree here is 2, so I got to do one more step. All right, this degree is 2, degree 2, degree 2. So I got to do one more iteration of the division algorithm. Right, so what do I need to multiply x squared minus x plus 3 to get x squared as a leading term? Just 1. So x squared minus x plus 3. Flip the signs, minus, plus, minus. Add them together, and I get minus 4x plus x is minus 3x, and then plus 0. So this is degree 1. This is degree 2. right? So so that's my quotient and remainder. Or so that's my final step. So I need to end here where that's my remainder, and that's my quotient. So what we get is, as a final answer, this is equal to the quotient, which is x plus 1, plus the remainder over the divisor. Okay, final answer there. So that's number 19. Why don't we do, let's see. Let's do 23. So x to the 6th plus x to the 4th plus x squared plus 1 over x squared plus 1. All right, so let us set up the algorithm for division. And don't leave any missing terms. So there's no x to the 5th here, so we'll put 0x to the 5th plus x to the 4th. No x to the 3rd term, so we'll put 0x to the 3rd plus x squared plus no x term, so we'll put 0x plus 1. Okay, again, use 0x to the I if x to the I does not appear. In the numerator. And we're dividing this by x squared plus 1. All right? You can leave out the 0 there if you want, or, you can put it in. Then just leave it out. You don't need it there. Here, it's nice for sort of a bookkeeping purposes. Okay, so I want to multiply this by x to the 3rd. X to the 4th. Multiply x squared by 1 at plus 1 times x to the 4th to get x to the 6th as the leading term. So this gives me x to the 6th plus x to the 4th, and put that underneath, the x to the 4th term here. Right, so x to the 6th plus x to the 4th, flip the terms, and this is 0, 0, 0. So I'm just left with, and I'll bring down the remaining terms here, so that's just 0, just x squared plus 1. Right, so just bringing all that down, I get x squared plus 1. Now I just multiply this by 1. And that gives me x squared plus 1. I flip my signs, and I get 0. Okay, so this tells us that so this is remainder 0. Remainder quotient. Look at the difference in degrees here. This is degree 6, and this is degree 2. That says I'm going to need 5 iterations at most. So 6 minus 2 is 4. So that says I'm going to need, at most 5 iterations of the division algorithm. But I only needed 2 here. And basically what happened is that x squared plus 1 divides evenly into that numerator because I got a remainder of 0. So in the end, what I get is that this is equal to just the quotient, x to the fourth plus 1. And you can leave out the remainder thing, right? It's plus 0 over x squared plus 1. You can leave that out because it's just 0. Right? Therefore we have this, that x to the 6th plus x to the 4th plus x squared plus 1 over x squared plus 1 is equal to this, which also implies that x to the 6th plus x to the 4th plus x squared plus 1 is equal to this. So we actually have a factorization. It's not necessarily well, no, actually it is. That's actually a complete factorization of this polynomial. This fact doesn't factor anymore, nor does that over the real numbers. So that's a nice problem. Came out well. All right, so, do these ones on your own. Try number 21 on your own. You can try some of the other ones as well. They also have this thing called synthetic division. You don't have to worry about synthetic division. It's just sort of a shorthand notation, but it's not applicable in every situation. So, don't really. If you want to sit and read it, you can, but it's not really that important. Okay, so that's a good selection of problems there. In general, how to factor polynomials, how to find the roots of polynomials, these are very difficult questions. And, we're really just scratching just the bare surface of the thing, of the topic. It's a huge topic, and, the basic answer to the question of, well, how do you factor this polynomial is we don't know. Because you hardly ever will know. It's hard to find the roots of polynomials. It's hard to find the factorizations of polynomials. These are all what's known as computationally difficult problems. But there are situations in which you do, and those are important situations. Okay. So moving on to section 3.5, I know some of you already know what we're going to talk about here because I've seen you sort of do it in the homework once in a while. But, let's talk about it some more. I'm sure some of you haven't seen it. Complex roots, or zeros of polynomials. So first of all, some terminology. P of x. So let P of x be a polynomial. Okay, so a P of x is a polynomial. It's not an equation. It's a polynomial, right? Like 3x squared plus 2x minus 1. That's a polynomial. Right? So, a solution is a term that you use with an equation. Okay, a solution to the equation P of x equal to 0 is called either a root of P of x or a 0 of P of x. I think root's the better term. Okay, so polynomials don't have solutions. polynomial equations have solutions. The solutions, given a polynomial, the solutions of the associated equation are called the roots of the polynomial, or the zeros of the polynomial. Okay, these are very slight differences, but I mean, it's good to use the right term in the right situation. All right. So given a polynomial, p of x, the real roots to the polynomial are the x-intercepts of the graph y equals p of x, because these are where 0 is equal to y is equal to p of x. So when you've got this polynomial, y equals x minus 1 squared minus 4, right? So this is a parabola, right, whose vertex is down at 1, negative 4, whose y-intercept, where x is equal to 0, is at 3, or negative 3, and whose x-intercepts, so this is the polynomial if you multiply it through, it's x squared minus 2x plus 1 minus 4 minus 3, which is equal to x minus 3x plus 1. So whose x-intercepts are at 3 and negative 1. So a graph of this parabola is here. Not a very good one. Let's try it again. Better. All right, so the x-intercepts are at negative 1 and 3, because that's where this quantity is equal to 0. Right? That's where the x-intercepts are. That's where the real roots of the polynomial are. Right? That's where the x-intercepts are, and that's where the real roots of the polynomial are. So I mean, the graph is reflecting something important about the polynomial. Okay, but sometimes a parabola doesn't have to have any x-intercepts at all, right? I mean, I could take this parabola and shift it above the x-axis, right, and then you won't have any x-intercepts at all. So some polynomial functions don't have x-intercepts, but that doesn't mean that it doesn't have roots in some other number system. So, for example, y equals x minus 1/2 squared plus 3/4. So this is 1/2, and that's 3/4 on the y-axis. So here is the vertex of the parabola, and this is the polynomial x squared minus x plus 1. So the y-intercept actually is at 1. And this polynomial looks like, this parabola for this quadratic function looks like this. Right? So no x-intercepts. So no real roots. But is that the end of the story? And no, the answer is no. So define a new number, I equal to the square root of -1. All right, now you could say, well, you know, there's no such number. Well, yeah, there is no such real number, but you know, you can just call it a number. There's nothing to say that you can't, right? I mean, numbers in some sense kind of aren't. I mean, depending on what sense you're talking about, they're not real. I mean, you can't touch them and grab them, right? I mean, you can't feel too. You know, nobody's ever seen the number 3. I mean, I can see 3 potatoes sitting on the table that I'm going to cut up and fry, right? But that's not the number 3. That's 3 potatoes. I mean, they're not tangible things, numbers. You know, and then you have these weird numbers like the square root of 2 and pi and whatever. And, you know, they don't really have any physical meaning either. You know, you measure things using those numbers, and that's all well and good. But that's not the number itself. So this is no stranger than that. This number I, the square root of -1. You say, okay, it's a number. Now, one can make up a number and make up all kinds of things and talk about those things, but the question is it a worthwhile idea? And an idea is worthwhile, you know, I mean, this is a question of aesthetics, right? I mean, you know, what makes an idea worthwhile? If the idea says something nice, if it tells a nice story, if it solves practical problems. You know, these are what makes ideas worthwhile. Numbers are a great idea, the original integers, right? Because, you know, I mean, when people wanted to total up bushels of barley and all kind of, you know, jugs of wine and all kind of stuff like that, you know, I mean, they used numbers to keep track of things. I mean, then doing arithmetic aids commerce and therefore civilization, right? So, I mean, it's a worthwhile idea. So is this a worthwhile idea? You know, the short answer is, oh, yes. In some sense, numbers that use this idea are more beautiful than the original numbers. I don't think we're going to be able to get into it, but here's just a taste. So as a consequence of this definition, the square root of any negative number is equal to, well, it's the square root of 4 times -1. Right? And remember, square roots distribute over multiplication, not over addition, over multiplication. So this is square root of 4 times square root of -1, that's 2, and this is I. Square root of things that are not perfect squares, you know, so square root of -3, well, we just write it as square root of, 3 times -1. You just write root 3 times I, and that's fine. Root 3 is a real number, and 2 is a real number, and we're multiplying it by this thing, I. Okay, so as a consequence of this definition, I, right, the square root of any negative number becomes something that we can talk about in terms of this new thing called I standing for imaginary. So now a complex number is a number of the form a plus b times I, where a and b are real numbers. Okay, so for example, 3 minus 2i, 3 plus 2i, 7i, just a real number like 8 or minus 8, that's a complex number. Root 2 plus I, root 2 minus I, etc., etc. Okay, so these are a combination of a real number plus a multiple of I. And those are called complex numbers. And now we in no way can prove this, but just to tell you what it is, the fundamental theorem of algebra is the following. So proving the fundamental theorem of algebra is like first year in graduate school in mathematics. There's like a couple different ways you can get to the proof of the fundamental theorem of algebra. There's an algebraic proof, and there's a proof that uses calculus. But the basic of the fundamental theorem of algebra is that every polynomial of degree n has n roots, counting multiplicity. Counting multiplicities has n roots within the complex numbers. So, I mean, for real numbers, that's totally not true. Like a polynomial of degree 7 can have 0 roots. No, I'm sorry, that one has to have one. A polynomial of degree 8 could have 0 roots, or this one here, this polynomial of degree 2, doesn't have any roots. The fundamental theorem of algebra says it has 2 roots, counting multiplicities. Right? Because sometimes, you get polynomials like this, x minus 2 to the third times x plus 1. So this has 2 as a root of multiplicity 3. And minus 1 is the root of multiplicity 1. So, multiplicities, give you this adding up to n, right? 2 is the root of this polynomial 3 times because it factorizes as x minus 2 to the third. And then negative 1 is a root just once, multiplicity 1. But that's, just a little peek into, why these complex numbers are special. What is sort of deficient about the real numbers in some algebraic senses, in some calculus type senses, and in some geometric senses. What deficiencies you have in the real numbers are, accounted for by thinking about complex numbers. And the first one is this business with polynomials. All right, so for example, so the roots of any polynomial of degree 2 are obtained from either, completing the square, or using the quadratic formula, where, taking the square root of a negative number is no longer a problem. So for example, going back to this, polynomial over here, right, so if we use the form for completing the square, so x minus 1/2 squared equals 0 plus 3/4 equals 0. Move the 3/4 over there. Now take the square root of both sides. Right? This is no longer a problem here. Right? This square root of negative 3/4. Right? Over here we get absolute value x minus 1/2. Over here you get root negative 3 over root 4. So absolute x minus 1/2 is equal to, so this is root 3i. That's 2, and this is I. Root 3 over 2i. So x minus 1/2 is equal to root plus or minus root 3 over 2i. So x is equal to 1/2 plus root 3 over 2i. Or x is equal to 1/2 minus root 3 over 2i. Those are your two roots. Or you could have used the quadratic formula. So x is equal to minus b plus or minus the square root of b squared minus 4ac over 2. So x is equal to minus b is plus 1. Plus or minus b squared is 1 minus 4ac is just 4 over 2, over 2a. But a is just 1, so x is equal to this. So x is equal to 1 plus or minus square root of minus 3 over 2. So x is equal to 1 plus or minus root 3i over 2. So x is equal to 1 plus, 1/2 plus root 3 over 2i, or 1/2 minus root 3 over 2i. So same idea. All right, so you can always find these roots now, and notice we've got two of them, right? The two coming by virtue of that plus or minus business. We found those two roots of this polynomial of degree 2, and you can use either process, the process using the quadratic formula or the process using completing the square, and you won't run into problems because we don't care about taking the square root of a negative number anymore. We know how to deal with it with this new thing, I, our new friend. I called, imaginary. Our new friend. So, do I have it? Where is it? I get this funny little cartoon to show you. Oh gosh, where did it go? I'll find it later. I'll post it after class. Alrighty. So more generally, with polynomials of higher degrees, definition. Given a complex number z equal to a plus bi, its conjugate is a minus, well, let's not use the z, is a minus bi. And of course, that number is different than a plus bi. Right? Because as long as that b isn't 0, then we're okay. It's actually a different number. So, for example, 1/2 plus root 3 over 2i conjugate is 1/2 minus root 3 over 2i, like in that last example. 3i conjugate is minus 3i. You just negate the imaginary term. And 6 conjugate is 6. Right? So when you want to conjugate a real number, it's just the same number back. If you want to conjugate just a purely imaginary number without the real term, it's just negation. And then if you've got both terms, real plus imaginary, then you just negate the imaginary bit, leave the real bit alone. And the fact is that, so for any polynomial with real coefficients, complex roots come in conjugate pairs. That is, if a plus bi is a root of p of x, then so is a minus bi. Right. Well, then this is also a root of p of x. So here's an example. I mean, again, there's examples aren't, not again, but I mean, an example isn't a proof, but, you know, and this is not a fact that is really hard to prove. I mean, giving an actual proof of this is not difficult, but it's not what, you know, this sort of class is based upon. And it just takes some time that we're just not going to spend. So let's look at the polynomial x to the fourth minus 5x squared plus 4 is p of x. All right, so we look at the equation with this. Well, you know, this has just got a fourth and a squared term, right? So this is x squared squared minus 5x squared plus 4, right? This trick of using the x squared as your variable x. Right, so this is x squared minus 4 x squared, oops, long polynomial plus, there we go, x squared plus 4x squared plus 1 equals 0. Right, so this means x squared plus 4 equals 0, or x squared plus 1 equals 0. And this means that x squared is negative 4, or x squared is minus 1. And, you know, if you're only looking at real roots, you just say, okay, we're done. Doesn't have any real roots. And, you know, that's appropriate in lots of instances, like when you're actually doing measurements, right? I mean, when you're measuring lengths and areas and things like that. In this case, you don't talk about complex numbers because, you know, they don't make sense as areas and as lengths and things like that. But, you know, in other situations, you can. So this means that x is plus or minus, right, square root of negative 4. X is plus or minus the square root of minus 1. So x is equal to, and what's this? 2i. Or negative 2i. Or, and this one is just I. Or negative I. So right? We have the roots come in two complex conjugate pairs. The four roots, polynomial of degree 4, has no real roots, 0 real roots, but I mean, when you look at complex numbers, you got 4 roots. 4 distinct roots of multiplicity 1. So the 4 roots of the polynomial of degree 4 come in two complex conjugate pairs. In two conjugate pairs. So since complex roots come in twos, right, come in pairs, what about a polynomial of odd degree? A polynomial of odd degree, by the fundamental theorem of algebra, right, is going to have, that odd number of roots. But since the complex roots come in pairs, one of those roots has got to be real. So as a consequence, a polynomial with real coefficients and with odd degree must have at least one real root. Right? So either one real root, so for example, polynomial of degree 3 has either one real root, two complex conjugate roots, or 3 real roots. Again, counting multiplicities. So for example, y equals x to the third plus x squared plus x plus 1. That's this. Actually, what is it? I think it's right here. I don't know what the graph looks like on this one. Right, so a polynomial of degree 3, right, always has this type of behavior. Right, it goes to negative infinity off to the left and positive infinity off to the right. So the graph of a polynomial of degree 3. And therefore, it has to have one x-intercept. Right, so a graph that looks like this has one real root and two complex roots. Something like that has 3 real roots. Right, so not that you can necessarily always find what that real root is. You can. There's things called Cardano's equations, but they're really very complicated. So for a degree 3 polynomial, you can always find what that root is, but for degree 5, no. So degree 3, degree 5, degree 7, they always have at least one real root because the complex roots come in pairs. So they only account for an even number of roots. Okay, so that is all for this section. Just a few homework problems for discussion for tomorrow. Where did they go? 19 to 35 odd. So we'll do some of those tomorrow, and I'll post a hand-in assignment for section 3.5 after class, and I'll send you the usual email, of course. Okay, have a good day, everybody. I'm in my WebEx room from 11:30 to 12:30 if you want to stop by. See you tomorrow, otherwise.